Welcome, gentle listener. We find ourselves together in a moment of quiet presence, where the soft murmur of the world outside meets the calm within. Perhaps you are nestled beneath a blanket, listening to the distant patter of rain against the window, or maybe you're resting in stillness as twilight settles like a soft sigh over the land. Have you ever paused to consider the gentle, ever-changing presence of the weather? Not as a subject of forecast or small talk, but as a living, breathing dialogue between the earth and the sky. A continuous, graceful dance of air, water, and light that has been unfolding since long before we walked this world. It is a conversation written in the language of breezes and clouds, of mist and sunlight, of stillness and storm. A conversation that needs no words, only presence. We are about to embark on a journey, not of distance, but of depth. A journey into the quiet heart of how weather works. Not through complex equations or frantic urgency, but through wonder, through story, through the soft and steady rhythms of nature's own intelligence. This is an invitation to witness the world as a whole, to see how a single ray of sunlight falling on a distant ocean can set in motion winds that will eventually whisper through the trees outside your window. How the breath of the atmosphere, moving in great, invisible rivers, connects every living thing in one continuous, breathing system. But first, take a breath and tell me, where are you joining in from tonight? And what is the weather like? Are you joining in on a chilly evening, wrapped in the comfort of a blanket? Or are you outdoors, perhaps on a nice sunlit balcony, or by a window with raindrops slowly falling? Wherever you are, whatever the sky holds for you tonight, I invite you to settle in, to breathe deeply, and to allow your awareness to soften like evening light. This is not a lesson to be memorized, but a landscape to be felt. A reminder that you are not separate from the air you breathe or the rain that falls. You are part of this delicate, dynamic balance, a living participant in a system both vast and intimate. So let your thoughts settle like dust in still air. Release the weight of the day and allow your mind to grow quiet, open, and receptive. There is no need to strive, no test to pass, only an opportunity to listen to the whisper of the wind, the rhythm of the rain, the warmth of the sun, and in doing so, remember your place within this elegant, ever-unfolding whole. We'll move slowly, like a soft front settling over the hills. We'll explore how the world breathes, how clouds form like thoughts in the mind of the sky, and how every change in the air is part of a larger, harmonious order. And perhaps, by understanding the gentle workings of the world outside, you may also sense a corresponding calm within, a stillness as deep and sure as the horizon after rain. If you're ready, let's begin. Let's turn our attention softly and without effort to the quiet miracle of the air around us. Imagine, if you will, that you are not lying in a room, but are instead cradled in the palm of a vast, invisible ocean. This ocean has no shore, and its depths are above you, stretching up and up for hundreds of miles until it finally fades into the utter blackness of space. This is our atmosphere, a great, gentle blanket of gas that envelops our entire world. And it is within this fluid, ever-moving medium that the eternal, silent ballet of weather is performed. It is a show of breathtaking complexity and profound simplicity. A story written in the language of light and shadow, of heat and cold, of pressure and release. It begins not with a clap of thunder, but with a whisper. The whisper of photons, tiny particles of energy that have traveled 93 million miles from our sun, crossing the void in a straight, unwavering line for 8 minutes until they finally gently rain down upon the Earth. This sunlight, this constant, generous stream of energy, is the sole engine of our weather. It is the invisible hand that stirs the air, that lifts the water, that paints the sky with clouds and fills the silence with the sound of wind. But this hand does not touch the Earth evenly. Our planet is a sphere, gracefully curved, and this simple, beautiful geometry dictates everything. Think of shining a flashlight directly upon a table. You get a bright, concentrated circle of light. Now tilt that flashlight so the beam glances across the surface. The light spreads out, becoming dimmer and weaker. This is the fate of sunlight at the poles. The equatorial regions of our world, the warm belt around its middle, are like that direct circle of light. They receive a focused, intense dose of solar energy day after day, year after year. The North and South poles, however, are only ever brushed by a glancing ray, the same amount of energy stretched thin over a much larger area. This creates a fundamental imbalance, a difference in temperature that nature, in its infinite and patient wisdom, constantly seeks to resolve. The atmosphere strives for equilibrium, for a state of even temperature and pressure across the globe, but the sun's relentless, uneven heating makes this impossible. It is this beautiful, eternal frustration, this constant attempt to settle accounts that can never quite be settled, that gives us our weather. The process begins so gently. The air above the tropics, warmed by the land and sea below, itself becomes warm. And warm air, like a hot air balloon, becomes less dense. It grows light and buoyant, and it begins to rise. This is not a violent motion. It is a slow, majestic ascent, a great sighing exhalation of the planet. Trillions upon trillions of air molecules begin an upward journey, drifting into the cooler, higher layers of the atmosphere. This rising air creates a slight emptiness at the surface, a gentle deficit of mass, known as a low-pressure zone. Meanwhile, the air over the subtropics, cooler and denser, settles and sinks, creating areas of high pressure. Air, like water, flows from high pressure to low pressure, and so a movement begins. A gentle wind starts to blow, flowing from the areas of sinking dense air toward the areas of rising light air. This is the birth of a wind. But on a spinning planet, the path of this wind is not straight. The Earth rotates from west to east, and this rotation imparts a subtle force to any moving object, a force known as the Coriolis effect. It is not a true force, but rather an artifact of our moving perspective, much like how a carousel makes it difficult to throw a ball in a straight line to someone across from you. In the northern hemisphere, this effect deflects moving air to the right. In the southern hemisphere, it deflects it to the left. So the wind rushing toward the equatorial low pressure does not flow straight south or north, it is turned sideways, becoming a reliable, steady breeze from the northeast in the northern tropics and from the southeast in the southern tropics. These are the trade winds, the great, faithful currents that for centuries filled the sails of explorers and merchants, winds born from the simplest of principles. The sun heats the earth unevenly, and the air must move in response. This rising and falling of air on a global scale creates massive, slow-moving cells of circulation that band the Earth like a series of nested, invisible conveyor belts. The tropical cell, where air rises at the equator and sinks near the 30-degree latitude mark, is called the Hadley cell. Further poleward, between 30 and 60 degrees, another set of cells, the Ferrel cells, operate in a more complex stance, driven by the interaction of the tropical and polar air masses. And near the poles, the polar cells complete the picture, with cold, dense air sinking and flowing outward at the surface. These great cells are the foundational rhythms of our planetary atmosphere, the deep, steady bass notes upon which all other weather is but a temporary and fleeting melody. They set the stage for everything that follows. They create the semi-permanent bands of high and low pressure that guide the paths of storms and the itineraries of fair weather. They are the reason why the world's great deserts lie along the 30-degree lines under the dry, sinking air of the Hadley cells, and why the temperate latitudes are so changeable, caught in the battleground between tropical and polar air. This global circulation is the great slow pulse of the planet, a breath that takes months to complete, a circulatory system for heat and energy that has been operating for billions of years, long before life itself learned to look to the sky and feel the wind on its face. It is the first and most important chapter in the story of how weather works, a story of balance, sought but never quite achieved, of energy constantly on the move, transforming itself from sunlight on water into the gentle breeze that rustles the leaves outside your window now. As we have seen, the sun's energy sets the great ocean of air in motion, creating vast rivers of wind that flow around our world. But wind is only one part of the story. The most visible and perhaps most poetic aspect of weather is the cloud, those floating cathedrals of vapor that drift and morph in the sky. Their birth is a story of transformation, a delicate dance between the air's capacity to hold and its willingness to let go. It begins, as all things do in this cycle, with the sun. Its rays fall upon the great blue expanses of the ocean, upon the moist soil of the forests, upon the glittering surface of lakes and rivers. This energy agitates the molecules of water, giving them the motion they need to break free from their liquid bonds and become individual, invisible particles, water vapor. This process, evaporation, is a silent, constant exhalation of the planet. Trillions of gallons of water are lifted, molecule by molecule, into the waiting embrace of the atmosphere every day, an endless upward flow that we cannot see, but upon which all life depends. The air absorbs this vapor, holding it invisibly within its gaseous mix. But the air is not an infinite vessel. Its capacity to hold water vapor is entirely dependent on its temperature. Think of warm air as a vast, spacious sponge, capable of absorbing and holding a tremendous amount of moisture. Cool air, by contrast, is like a small, dense sponge. It can only hold a little. This simple relationship is the key to everything that follows. Now, recall the warm, moist air at the equator, buoyant and full of vapor, beginning its slow, inevitable rise. As it lifts away from the warm surface, it enters the cooler realms of the higher atmosphere. The air expands as it rises because the pressure around it is decreasing, and as it expands, it cools. This is a fundamental law of physics. Expanding gases cool down. So the air, which started warm and moist, becomes cool. And as it cools, its capacity to act as a sponge diminishes. It can no longer hold all the invisible water vapor it once could. The vapor must change its state. It begins to condense, clinging to tiny, microscopic particles floating in the air. Specks of dust, grains of salt from ocean spray, spores, pollen, even particles of pollution. These tiny motes serve as condensation nuclei, providing a surface for the water molecules to gather upon. Countless molecules coalesce around countless nuclei, forming minuscule droplets of liquid water. Each droplet is so small that it would take millions of them to form a single raindrop. But together, in their billions and trillions, they become visible. They become a cloud. This is why we see clouds, not because water vapor itself is visible, but because when it condenses into these tiny droplets, they reflect and scatter sunlight, appearing to us as white, fluffy masses floating in the blue. The cloud is not a solid thing. It is a vast collection of these tiny droplets, a floating mist held aloft by the gentle upward currents of the air itself. The shape and type of cloud that forms tell a story about the conditions in the atmosphere. The high, wispy clouds we call cirrus are formed from ice crystals at great altitudes where the air is thin and bitterly cold. They are the scribbles of the wind, written 5 miles up. The low, layered stratus clouds are like a gentle gray blanket formed when a large, stable layer of air is slowly lifted, cooling and condensing uniformly across the sky. They bring soft, drizzly rain and a muted, diffused light that can feel so peaceful and contemplative. And then there are the cumulus clouds, the classic cotton-like puffs that drift on a fair weather afternoon. These are formed by convection, the same process that drives the global winds, but on a much smaller local scale. A patch of ground is heated more than its surroundings by the sun. The air above it warms and begins to rise in a discrete column, or thermal. As it rises and cools, the water vapor within it condenses, forming a single puffy cloud that marks the top of that invisible rising column of air. You can often see them growing, their flat bases all at the same altitude, the precise level where the rising air has cooled enough to reach its dew point and begin condensation, while their tops billow upward as the thermal continues to rise. They are the friendly giants of a summer sky, drifting lazily on the breeze. But sometimes the process is anything but lazy. When the atmosphere is unstable, when there is a great deal of warm, moist air at the surface and much colder air aloft, the rising thermals can be incredibly powerful. They can race upward at tremendous speeds, carrying vast quantities of moisture high into the atmosphere. The tiny water droplets are carried upward into the frigid heights where they freeze into ice crystals. These ice crystals and supercooled water droplets collide within the turbulent updrafts, growing larger and heavier. This is the birth of a cumulonimbus cloud, the great thunderhead. It is a cloud of immense power and vertical extent, its flat base perhaps only a kilometer above the ground, but its anvil-shaped top spreading out over 15 kilometers high, where the winds smear its ice crystals across the sky. This cloud is a factory for weather, a system of immense energy driven by the relentless heat engine of the sun. Within it, the collisions of ice and water create electrical charges, positive charges separating from negative charges. The difference in these charges builds until the resistance of the air itself breaks down, and a brilliant, jagged bolt of lightning rips the sky, a momentary equalization of energy that we see and hear as a thunderclap. The frozen particles, having grown too heavy for the updrafts to support, begin to fall. They may melt into raindrops or remain as hail, rattling through the cloud and accumulating until they plummet to the earth. This is weather at its most dramatic, yet it is born from the very same principles as the gentlest fog or the most harmless puff of white, the rising and cooling of air, and the beautiful, inevitable transformation of invisible vapor into visible water. Now, let us follow the journey of that which has condensed from the invisible, the water that has gathered itself into a cloud. For a cloud is not an end, but a way station, a temporary resting place in a much longer, eternal voyage. The tiny droplets, each one a perfect sphere reflecting the entire world in miniature, drift and dance within their airy home. They are so small, so lightweight, that the gentlest upward current is enough to keep them suspended, floating in a state of beautiful equilibrium between the pull of gravity and the push of the air. They move with the wind, a great collective of moisture traveling across continents, their form constantly shifting as some droplets evaporate back into vapor and new ones condense to take their place. It is a peaceful existence, this drifting. But nothing in nature remains static for long. Change is the only constant. And for the cloud, change often comes from a gentle nudge, a slight alteration in its environment. Perhaps the cloud drifts into a slightly drier patch of air, and the edges of the cloud begin to fray, the droplets evaporating back into invisibility as if the cloud itself is dissolving into a memory. Or perhaps the air continues to cool, or more moisture is added, and the droplets begin to coalesce. They bump into one another in their gentle drift, merging, combining, growing ever so slightly larger and heavier with each union. This process, known as coalescence, is a slow, patient dance. For precipitation to begin, for rain to fall, for snow to flutter down, these droplets must achieve a certain mass, a certain weight, that finally tips the balance against the upward force of the air. It is a threshold, a moment of decision for the water. In the warm clouds of the tropics, this is often enough. Large droplets form and begin to fall, colliding with smaller ones on their way down, growing into full-sized raindrops. But in colder clouds, where ice crystals coexist with supercooled water droplets, a different, more efficient process takes hold. It is known as the Bergeron process. The air pressure around an ice crystal is slightly lower than that around a water droplet. This causes the water droplets to evaporate ever so slowly, and the vapor then deposits itself directly onto the ice crystal. The ice crystal grows, its intricate six-sided lattice structure forming a snowflake, fed by the sacrifice of the surrounding droplets. The snowflake grows heavier, and when it can no longer be supported by the updrafts, it begins its long, slow descent to the earth. On its way down, it may pass through warmer layers of air and melt, arriving at the ground as a raindrop. Or it may remain frozen, landing as a delicate, unique crystal, each one a tiny masterpiece of atmospheric geometry. And so the water returns. It falls. After its journey into the sky, after its transformation from vapor to liquid or ice, it comes back to the earth. This is precipitation, the completing arc of the Great Water Cycle. It can take many forms, each with its own character and its own gentle music. There is rain, the most common form, a steady pattering on leaves and rooftops, a soft drumming that can soothe the soul. There is drizzle, a mist-like rain of very small droplets, hanging in the air like a veil, softening the edges of the world and leaving a fine, shimmering coat of moisture on every surface. There is snow, the silent fall of ice crystals, muffling sound and painting the world in a blanket of pure white, each flake a temporary wonder. There is sleet, which are raindrops that have frozen during their fall, making a tiny ticking sound as they strike a window pane. And there is hail, the occasional product of a powerful thunderstorm, where ice pellets are tossed up and down repeatedly in the violent updrafts, adding layer upon layer of ice until they are too heavy to be supported and fall to the ground. But most often, it is the gentle rain that returns the water to the earth, seeping into the soil to feed the roots of plants, collecting in streams and rivers that eventually find their way back to the oceans, or pooling in quiet lakes to await once more the sun's energizing touch. This completes the cycle. The sun provides the energy to lift the water. The atmosphere, with its currents and temperatures, provides the pathway and the conditions for its transformation and transport. And gravity, the constant, patient force, eventually brings it home. It is a cycle without a true beginning or end, a loop that has been turning for billions of years. The water that now feeds the ancient redwood trees may once have been part of a cloud that drifted over a prehistoric ocean. The same molecules have been cycled and recycled through the ages, through the great systems of our planet. This is the hydrological cycle, the planet's way of breathing, of circulating its most vital resource. It is a system of sublime balance and profound simplicity, a constant, gentle process that shapes our landscapes, dictates the rhythms of life, and provides the fresh water that is the basis of all we know. The weather we experience from day to day, the sunshine, the clouds, the rain, the snow, is simply our local, temporary experience of this global, eternal cycle. It is the atmosphere's way of moving heat and moving water, of seeking a balance that it never quite achieves. And in that beautiful, eternal striving, it creates the conditions for life itself to flourish on this blue and green world, spinning silently in the vastness of space. Let us now turn our attention to the gentle forces that guide these vast movements of air and water, the invisible boundaries that shape our daily weather, and the quiet local breezes that whisper around us. For while the great global cells set the stage, the performance we see outside our windows is directed by more intimate and immediate actors. Imagine the atmosphere not as a uniform blanket, but as a fluid made of distinct bodies, each with its own personality, its own temperature, its own humidity, its own density. These are air masses, vast domes of air that can stretch for thousands of miles, and they are the fundamental characters in the story of our weather. They acquire their characteristics not from themselves, but from the surfaces over which they linger. An air mass that forms over the cold, frozen expanse of the Arctic will become cold, dry, and dense. We call this a continental polar air mass. One that forms over the warm waters of the tropical Atlantic will become warm, moist, and buoyant, a maritime tropical air mass. They can sit for days or weeks, settling into their identity, becoming what the geographers call source regions. They are like great, slow-moving giants, resting and gathering their strength. But these giants do not stay still forever. The same global wind patterns we discussed earlier, the prevailing westerlies and the trade winds, eventually nudge them into motion. They begin to drift, these colossal domes of air, moving away from their source regions and journeying across continents and oceans. And as they move, they begin to change the landscapes over which they pass. When a cold, dry, continental polar air mass moves southward over the autumn landscape, it brings with it crisp, clear skies, chilly nights, and the sharp, clean air that feels so invigorating. It is a giant of clarity and cold. When a warm, moist maritime tropical air mass moves northward, it brings humid, hazy days, soft, warm nights, and the promise of rainfall. It is a giant of warmth and growth. Our weather from day to day is largely the story of which air mass is currently residing over us, and the gentle, inevitable conflict that occurs when one giant meets another. For these air masses do not mix easily. They are of different densities, different temperatures, different essences. They are like oil and water, and where they meet, a boundary forms. This boundary is a front, and it is along these fronts that much of our most interesting weather is born. The meeting of two air masses is a slow, graceful dance, not a violent collision. Because cold air is denser, it tends to stay close to the ground, acting like a wedge. The warmer, less dense air is forced to rise over this sloping ceiling of cold air. And as we know, rising air cools, and cooling air condenses its moisture. So along these frontal boundaries, clouds form. The type of front is defined by which air mass is advancing. which giant is actively moving and displacing the other. When a cold air mass is advancing, pushing underneath the warm air and lifting it up, we have a cold front. The slope of this front is often quite steep, leading to a relatively rapid and forceful uplift of the warm air. This can create a narrow band of dramatic weather. Towering cumulonimbus clouds, heavy but short-lived rainfall, sometimes thunderstorms, and a noticeable drop in temperature and humidity after the front has passed as the cold air settles in. It is a swift, decisive change. A warm front, by contrast, is more gentle and patient. It occurs when warm air is advancing, but because it is less dense, it cannot easily displace the cold air. Instead, it slowly rides up and over the retreating wedge of cold air. The slope is much more gradual, often stretching for hundreds of miles. The cloud formation happens slowly and at high altitudes. First, wispy cirrus clouds, then a thickening veil of cirrostratus that creates a halo around the sun or moon, then a lowering deck of altostratus that dims the sunlight, and finally a thick blanket of nimbostratus that can bring hours or even days of steady, gentle, widespread rain or snow. The passage of a warm front is a slow, lingering affair, a gradual warming and increasing humidity. And then there are the local winds, the small-scale breezes that are the atmosphere's whispers. These are not driven by global patterns, but by the daily cycle of heating and cooling right here, on the ground. Consider the sea breeze. On a sunny day, the land heats up much more quickly than the water. The air above the land warms, becomes buoyant, and begins to rise. This creates a local area of low pressure at the surface over the land. Over the cooler water, the air remains denser, creating a relative area of high pressure. Air flows from high pressure to low pressure, and so a cool, gentle breeze begins to blow from the sea onto the land. It is nature's air conditioning, a welcome relief on a warm afternoon. At night, the process reverses. The land cools down much more rapidly than the water. The air above the water is now relatively warmer and begins to rise, creating a low pressure over the water. The cooler, denser air over the land then slides outward toward the water, creating a land breeze. In the mountains, a similar process creates valley and mountain breezes. By day, the sun heats the mountain slopes, which heats the air adjacent to them. This warmed air rises, drawing air up from the valley below, a valley breeze. At night, the slopes cool rapidly, chilling the air nearby. This dense, cool air then drains downslope, flowing like an invisible river into the valley below, a mountain breeze or katabatic wind. These are the quiet, rhythmic breaths of the landscape itself, a daily pulse of air that is as reliable as the sunrise and sunset, a testament to the simple, beautiful physics that governs our world, from the grandest global gale to the softest sigh of wind through the pines. Having observed the intimate dance of local breezes, the sea sighing onto the land by day, the land exhaling back over the water by night, the mountains drawing the valley's air upward to the peaks and then releasing it back down the slopes under the cover of darkness, we begin to see a larger, more serene pattern emerge. These are not random, chaotic events, but rather the consistent, predictable pulses of a planetary system breathing in and out with the steady rhythm of the sun's daily journey. This rhythmic breathing, when observed not over days or weeks, but decades and centuries, reveals the true character of a place. It reveals its climate. While weather is the atmosphere's fleeting mood, changing from hour to hour and day to day, a sunny morning giving way to a showery afternoon, a crisp autumn day preceding a damp, foggy night, climate is the atmosphere's enduring personality. It is the long-term average of all these moods, the statistical summation of countless days of sunshine and rain, heat and cold, wind and calm. It is the reason why a palm tree thrives in the steady, warm embrace of a tropical shore, but would perish in the deep, frozen winters of a continental interior. climate is the story told by the data of generations, the pattern that allows a farmer to know, with reasonable certainty, the best week to plant his seeds. Or a city to design its buildings to withstand the prevailing winds and the weight of expected snow. This personality of a place is shaped by a beautiful and complex interplay of factors, each one a thread in the tapestry of climate. The most fundamental, of course, is latitude, a location's distance from the equator. This determines the angle at which the sun's rays strike, and thus the intensity and consistency of the solar energy received. The equatorial regions, basking in direct sunlight year-round, develop the warm, stable personalities of the tropical climates, where the concept of winter is unknown, and the daily rhythm of temperature is often more pronounced than the seasonal one. The polar regions, by contrast, with their months of midnight sun followed by months of perpetual twilight, develop the harsh, frozen personalities of the ice-cap climates, where life clings tenaciously to the brief respite of a summer that never truly gets warm. Between these extremes lie the temperate latitudes, where the personality is more complex and dynamic. Here, the battle between the warm air masses pushing poleward from the tropics and the cold air masses pushing equatorward from the poles creates the changing seasons, the vibrant rebirth of spring, the lush growth of summer, the graceful senescence of autumn, and the deep dormancy of winter. The weather here is more variable, the moods of the atmosphere more changeable, making the climate one of transition and contrast. But latitude is not the only author of a region's climatic story. The presence of a large body of water, an ocean or a great lake, acts as a tremendous moderator, a thermal flywheel that resists rapid change. Water heats up and cools down much more slowly than land. This simple physical property bestows upon coastal areas a maritime climate, characterized by milder, less extreme temperatures. Winters are warmer and summers are cooler than at inland locations at the same latitude. The ocean's influence also brings higher humidity and more frequent precipitation, often in the form of gentle, drizzly rains that seem to hang in the air. A place like London or Vancouver embodies this personality. Its weather rarely extreme, its changes often gradual, softened by the proximity of the sea. In stark contrast, a location far inland, in the heart of a continent, experiences a continental climate. Here, cut off from the tempering influence of the water, the land heats dramatically in the summer sun, leading to scorching days, and cools just as dramatically in the winter, leading to bitterly cold nights. The annual temperature range can be enormous, a personality of extremes, of blazing heat and deep freezes. The air is often drier, and precipitation, when it comes, can be more intense but less frequent. The lay of the land itself, the topography, writes another chapter in the climatic story. Mountains are not merely passive features on the landscape, they are active players in shaping weather and climate. As a prevailing wind encounters a mountain range, it is forced to rise. As it rises, it expands and cools, leading to condensation, cloud formation, and precipitation on the windward side of the mountains. This is why the western slopes of the Cascade Range in North America or the southern Alps in New Zealand are among the lushest, rainiest places on Earth. They wring the moisture from the Pacific air masses. But once that air crests the mountain summit and begins to descend down the leeward side, a different process occurs. The air compresses, warms, and its relative humidity plummets. It becomes a dry, warm downslope wind. The leeward side of the mountain range lies in what is called a rain shadow, a region of significantly reduced rainfall. Here, deserts can form just a short distance from rain-drenched slopes. The Great Basin Desert in the western United States exists in the rain shadow of the Sierra Nevada mountains. This is how topography can carve starkly different climatic personalities into the landscape, placing a rainforest and a desert within sight of each other, separated only by a ridge of rock and ice. The altitude of a place also dictates its climate, with temperature generally decreasing the higher one goes, creating vertical zones of life. From warm foothills to cool forested slopes to alpine meadows, and finally to the frozen rocky peaks where the air is thin and the conditions are harsh, a world apart even from the valleys below. The intricate interplay of latitude, oceans, and topography weaves the world not in uniform gray, but in a magnificent tapestry of distinct climatic regions, each giving rise to its own unique biome, a community of life exquisitely adapted to the long-term rhythms of temperature and precipitation that define its home. These biomes are the ultimate expression of climate, the visible, living manifestation of the atmosphere's enduring personality. Imagine for a moment the steady, humid warmth of the equatorial regions, where the sun's energy is a constant, generous presence. Here, the climate fosters the tropical rainforest biome, a realm of breathtaking abundance and complexity. The air is thick with moisture and the scent of rich, decaying vegetation. Towering trees form a dense, multi-layered canopy that captures nearly all the sunlight, creating a world of dappled shade on the forest floor below. Life thrives in every conceivable niche. Countless species of plants, insects, birds, and mammals exist in a delicate, interconnected web. The rainfall is frequent and heavy, often arriving in predictable afternoon deluges that feed countless streams and rivers. There is no winter here, only subtle variations between slightly wetter and slightly drier seasons. The rhythm of life is set by the constant, warm humidity and the daily pulse of rain, a rhythm that has persisted for millions of years, creating one of the most diverse and vital ecosystems on the planet. Now, journey to the subtropics, around the 30-degree latitude lines, where the global atmospheric circulation creates zones of persistent high pressure and sinking dry air. This is the realm of the desert biome. The climatic personality here is defined by a profound lack of water. Rainfall is scarce, unpredictable, and often intense when it does arrive, quickly evaporating or running off the parched ground. The air is dry, and the temperature range is extreme. The sun beats down with relentless intensity during the day, heating the bare rock and sand, but the clear, dry air allows that heat to radiate back into space rapidly at night, leading to chilly conditions. Life in the desert is a masterclass in conservation and adaptation. Plants like cacti store precious water in thick, fleshy stems, protect it with sharp spines, and open their pores only at night to breathe. Animals are often nocturnal, spending the heat of the day buried in burrows and emerging to forage in the comparative cool of the night. The beauty of the desert is stark and subtle. The brilliant bloom of a wildflower after rare rain, the intricate track of a lizard in the sand, the profound silence broken only by the wind. It is a climate of extremes, and the life that calls it home is hardened and resilient, a testament to nature's ability to persist even under the most stringent conditions. Between these extremes of wet and dry lie the temperate biomes, whose personalities are shaped not by consistency, but by change, the glorious, predictable turn of the seasons. In regions with sufficient rainfall, the temperate deciduous forest biome emerges. Here, the climate delivers warm, humid summers and cold winters. The trees, oaks, maples, beeches, birches have adapted to this cycle by growing lush canopies of leaves in the spring and summer to capture the sun's energy, and then withdrawing their resources in the autumn, allowing the leaves to die in a final spectacular display of color before falling to the ground. The winter is a time of dormancy, a quiet period where life rests under a blanket of snow. The forest floor comes alive in the spring with a burst of wildflowers, racing to bloom before the canopy above closes and shades them out. This biome embodies the rhythm of renewal and rest, a deeply familiar cycle in the mid-latitudes. Where rainfall is less abundant, the temperate grasslands or prairie biome takes hold. The climate here is one of hot summers, cold winters, and periodic drought. The deep, rich soils support a sea of grasses and herbs, which are adapted to fire and grazing. The vast, open landscapes are home to herds of grazing animals and the predators that follow them. The wind is a constant presence, whispering through the grasses, which themselves form a dense mat of roots that holds the soil firmly in place. The sky seems larger here, a great dome under which the weather moves with visible purpose, from the terrifying beauty of a summer thunderstorm to the deep, silent cold of a winter blizzard. Moving poleward, the climate grows colder, the growing season shortens, and the winter's grip tightens. This is the domain of the boreal forest, or taiga biome, a vast coniferous wilderness that circles the globe just south of the Arctic Circle. The climate is one of long, bitterly cold winters and short, cool, moist summers. The trees, predominantly spruces, firs, pines, and larches, are perfectly shaped for this existence. Their conical forms shed heavy snow, and their evergreen needles allow them to begin photosynthesis immediately during the brief summer, without wasting time growing new leaves. The forest floor is a spongy carpet of mosses and lichens. This biome is a world of profound quiet in winter, broken by the cracking of trees in the deep cold, and a frantic burst of life in the summer, as migratory birds arrive to nest and countless insects hatch in the countless marshes and ponds that form from the melted snow. Finally, at the very poles, we find the tundra and ice cap biomes, where the climate is so cold that even in summer, temperatures rarely rise above freezing at the highest latitudes. The ground is permanently frozen in a layer called permafrost, which only thaws at the surface for a few brief weeks each year. Life is low to the ground, consisting of hardy grasses, mosses, lichens, and low-growing shrubs. It is a fragile ecosystem, adapted to a harsh existence, where a footprint or a tire track can remain visible for decades. The sun circles the sky in summer, never setting, and disappears entirely for the long polar night of winter, a time of unimaginable cold and stillness. Each of these biomes, from the steaming rainforest to the frozen tundra, is a direct and beautiful consequence of the climate that reigns there, a perfect illustration of how the grand atmospheric patterns we have been exploring ultimately write the story of life on Earth itself. Beyond the steady, defining rhythms of a region's climate, there exist larger, slower pulses that beat across oceans and continents, connecting distant parts of the globe in a delicate atmospheric dance. These are the climate oscillations, the multi-year cycles that gently modulate the background music of our weather, sometimes softening its melody, other times adding a dramatic crescendo. The most influential of these is the grand dance that plays out across the vast expanse of the tropical Pacific Ocean, a phenomenon known as the El Niño Southern Oscillation. It is a story of a seesaw in atmospheric pressure and a sloshing of warm water on a planetary scale, and its effects ripple through weather patterns across the globe. Under normal conditions, which oceanographers call enso-neutral, the prevailing trade winds blow steadfastly from east to west across the Pacific. These winds push the sun-warmed surface water westward, piling it up around Indonesia and Australia. This allows cooler, nutrient-rich water to well up from the depths along the coast of South America, supporting incredibly productive fisheries. The warm pool in the west heats the air above it, causing it to rise and creating abundant rainfall in the western Pacific, while the cooler east experiences drier conditions. This is the neutral state, a balanced and productive equilibrium. But approximately every 2 to 7 years, this delicate balance is disrupted. The trade winds weaken or sometimes even reverse. Without that constant westerly push, the great pile of warm water that was held in the western Pacific begins to slosh back eastward. It travels across the ocean basin, spreading out along the equator like a slow-motion wave. This massive redistribution of heat is the hallmark of El Niño, the little boy in Spanish, named for the Christ child because its effects are often most noticeable around Christmas time off the coast of Peru. As this warm water spreads east, it suppresses the usual upwelling of cold, nutrient-rich water along the South American coast. The fisheries there often collapse as the nutrients that feed the plankton at the base of the food web are cut off. But the effects are far more widespread. The immense heat released from this now vast central and eastern Pacific warm pool alters atmospheric circulation patterns on a global scale. It can trigger devastating droughts and wildfires in Australia and Indonesia, and severe flooding along the normally arid coasts of Peru and Ecuador. Its influence snakes along the jet streams, affecting weather patterns across North and South America, often bringing unusually warm and wet conditions to the southern United States and drier conditions to the north. The opposite phase of this oscillation is La Niña, the little girl. Here, the normal state is not just balanced, but amplified. The trade winds become even stronger than usual, relentlessly pushing even more warm water westward. This enhances the contrast between the warm west and the cool east. The pool of warm water around Indonesia becomes even deeper and hotter, fueling even more intense rainfall and tropical cyclone activity in that region. Meanwhile, the upwelling of cold water along the Americas intensifies, making the eastern Pacific even cooler and drier than usual. La Niña's global effects are often a mirror image of El Niño's. It can bring severe drought to the southern U.S., particularly the Southwest, and colder, snowier winters to the Pacific Northwest and the northern tier of the country. It can also contribute to a more active Atlantic hurricane season, as the stronger trade winds and specific atmospheric conditions over that basin become more favorable for storm development. These two phases, El Niño and La Niña, are the extreme swings of the ENSO pendulum. The entire cycle, from one El Niño to the next, typically lasts 3 to 7 years. It is a powerful reminder that our climate is not a static picture, but a dynamic system breathing in and out over years-long timescales, connecting the drought of an Australian farmer to the floodwaters of a Peruvian village through the invisible pathways of the atmosphere and the deep, warm currents of the world's largest ocean. ENSO is the most famous of these oscillations, but it is not alone. The North Atlantic Oscillation is a similar seesaw of atmospheric pressure, but between the Icelandic low and the Azores high pressure systems in the North Atlantic. Its fluctuations, which can change from week to week, primarily influence the weather of Europe and eastern North America. In its positive phase, with a strong pressure difference, the westerly winds across the Atlantic strengthen, bringing mild, wet winters to northern Europe and the eastern United States. In its negative phase, the pressure difference weakens, allowing cold Arctic air to spill southward, leading to harsh, snowy winters in both regions, the type of winters that produce memorable blizzards and deep freezes. Another important pulse is the Pacific Decadal Oscillation, PDO, a long-lived El Niño-like pattern in the Pacific Ocean, but one that lasts not for a year or two, but for 20 to 30 years. These decades-long shifts in ocean temperature can subtly amplify or suppress the effects of individual El Niño and La Niña events, acting as a slow background modulator of the climate system. These oscillations, these long-period rhythms of the ocean atmosphere system, are the reason why 2 winters in the same city can feel so profoundly different, even within the same overall climatic personality. They are the deep, slow breaths of the planet, and by learning to understand their rhythms, we gain a deeper appreciation for the beautiful, interconnected complexity of the system that brings us our daily weather and defines our long-term climate. They are the chapters in a much longer story, reminding us that the calm, predictable patterns we depend on are part of a much larger, ever-changing whole. Our journey through the atmosphere has thus far explored the troposphere, the bustling, weather-filled layer closest to the Earth where all life resides and where clouds form and rain falls. But if we were to continue upward, past the highest wisp of a cirrus cloud, we would enter a realm of profound stillness and immense importance, the stratosphere. This is a world apart from the turbulent weather below. The troposphere ends and the stratosphere begins at a boundary called the tropospause, which lies about 5 to 9 miles above the ground, depending on latitude and season. The most fundamental change that occurs here is a dramatic shift in temperature. In the troposphere, we are accustomed to temperature decreasing with altitude. That is why mountaintops are colder than valleys. But in the stratosphere, this trend reverses. The temperature begins to increase with altitude. This inversion creates an incredibly stable layer of air. There is no convection here, no rising thermals to form clouds and storms. The stratosphere is a vast, calm, and strikingly dry expanse. This stability is its defining characteristic, and it acts as a great lid, effectively containing the churning weather of the troposphere beneath it and preventing it from dissipating into the higher reaches of the atmosphere. The reason for this unexpected warming lies with a special molecule that exists in a thin, tenuous layer within the stratosphere: ozone. Ozone is a molecule made of 3 oxygen atoms, unlike the 2-atom oxygen molecule that we breathe. This layer of ozone, often called the ozone layer, is incredibly diffuse. If it were compressed to the pressure at the Earth's surface, it would be only about 3 millimeters thick. Yet, this fragile veil performs a function so critical that without it, life on land as we know it would scarcely be possible. The ozone molecule has a unique ability to absorb high-energy ultraviolet radiation from the sun. This is the same type of radiation that causes sunburn and can damage DNA, leading to mutations and cancer. When a UV photon strikes an ozone molecule, it is absorbed, and the energy from that photon breaks the molecule apart into a regular oxygen molecule and a single oxygen atom. This process converts the harmful ultraviolet energy into kinetic energy, heat. It is this continuous absorption and transformation of UV radiation that heats the stratosphere, creating the temperature inversion that defines it. In doing so, the ozone layer acts as a planetary sunscreen, filtering out the vast majority of the sun's most damaging UV rays and allowing life to flourish safely on the surface below. It is a magnificent, silent protection, a global shield maintained by the constant, invisible interplay of sunlight and a gossamer-thin layer of gas. The stability of the stratosphere has another profound effect. It allows certain substances, once they manage to enter this calm layer, to remain there for a very long time and spread across the entire globe. This is both a blessing and a curse. It is a blessing for the ozone layer itself, as the ozone molecules produced in the tropics can slowly circulate poleward, helping to maintain a protective blanket over the entire planet. However, this same stability meant that when human-made chemicals called chlorofluorocarbons, used in refrigeration and aerosol sprays, were released at the surface, They eventually drifted upward into the stratosphere. There, untouched by the weather that would normally break them down, they persisted. When exposed to the sun's UV radiation, they released chlorine atoms, which then acted as a catalyst in a destructive cycle. A single chlorine atom could break apart tens of thousands of ozone molecules before it was finally neutralized. This led to the dramatic thinning of the ozone layer, most notably over Antarctica, creating what became known as the ozone hole. The discovery of this phenomenon was a startling revelation of humanity's ability to impact the global atmosphere. But it also became a story of global cooperation and environmental success. The world came together to sign the Montreal Protocol, an international treaty to phase out the production of these ozone-depleting substances. And, slowly, painstakingly, the stratosphere is beginning to heal. The ozone hole is gradually recovering, a testament to the resilience of the natural system when given a chance, and a powerful reminder of our responsibility to understand and protect the delicate layers that make our world habitable. Above the stratosphere lie even more ethereal layers, the mesosphere, where temperatures plummet again and meteors burn up as shooting stars, and the thermosphere, where the air is so thin that the concept of temperature loses its everyday meaning, and the International Space Station orbits, passing from sunlight to shadow every 45 minutes. But for us, safely nestled at the bottom of the atmospheric ocean, the stratosphere and its precious ozone layer represent a crucial guardian, a silent, stable shield that makes the vibrant, weather-filled world of the troposphere below possible. It is a layer of profound peace and powerful protection, a reminder that the atmosphere is not just the source of our weather, but the guardian of our very existence. As the sun climbs each morning or sinks each evening, its light must travel through a much thicker slice of the atmosphere than when it is directly overhead. This long journey provides countless opportunities for the atmosphere to act not just as a medium for weather, but as a grand lens and a prism, sculpting sunlight into some of the most serene and breathtaking displays nature has to offer. This is the world of atmospheric optics, a gentle physics of light and water, of ice and air, that paints the sky with soft, silent masterpieces. It begins with the most common and yet most overlooked phenomenon, the blue sky itself. Sunlight, which appears white to our eyes, is actually composed of every color of the rainbow, each with its own wavelength. As this light travels through the atmosphere, it collides with the countless tiny molecules of nitrogen and oxygen that make up the air. These molecules are much better at scattering the short wavelength blue and violet light than the longer wavelength reds and oranges. This process, known as Rayleigh scattering, sends the blue light bouncing off in all directions, effectively filling the entire sky with a soft blue glow. We see this scattered blue light from every direction we look, and thus the dome of the sky appears blue. At sunset and sunrise, the light must travel through an even greater expanse of atmosphere to reach our eyes. By the time it arrives, most of the blue light has been scattered away, leaving behind the longer wavelengths of red, orange, and pink to paint the clouds and horizon in those glorious, tranquil hues that mark the transitions of the day. When the air holds not just molecules, but also tiny water droplets, the possibilities for beauty multiply. A cloud, which appears white, is simply a collection of droplets that are large enough to scatter all wavelengths of light equally, combining them back into white light. But sometimes, when the conditions are just right, the cloud's droplets can act like a multitude of tiny prisms. If the cloud is composed of very uniform small water droplets, and the sun is positioned directly behind you with the cloud in front, a miracle can occur. Light enters the droplet, reflects off its inner surface, and exits, being refracted or bent in the process. This refraction separates the light into its constituent colors, just as a glass prism does. When this happens across millions of perfectly lined droplets in the cloud, the result is a soft pastel band of colors painted onto the cloud itself. This is a cloud iridescence, a delicate and ethereal display of pinks, greens, and blues that shimmers like mother of pearl. It is a fleeting sight, often seen on the edges of newly forming clouds, a whisper of color that appears and vanishes within minutes, a secret gift for those who remember to look up at the right moment. Perhaps the most famous and majestic of all atmospheric optical phenomena is the rainbow. Its formation is a beautiful and precise dance of light and water. For a rainbow to appear, two elements must align. The sun must be shining behind the observer, and rain must be falling in front of them. Each individual raindrop acts like a tiny spherical prism. A beam of sunlight enters the drop, refracts and separates into its spectrum of colors, reflects off the inside back surface of the drop, and then refracts again as it exits. This double refraction and single reflection sends the light back toward the observer, but with its colors fanned out. Because this process happens at a specific angle, about 42 degrees from the path of the original sunlight, the rainbow always appears as an arc opposite the sun. The colors always appear in the same order: red on the outer part of the arc, followed by orange, yellow, green, blue, indigo, and violet on the inner curve. It is a personal phenomenon. No two people see exactly the same rainbow because each person is seeing light reflected from a different set of raindrops. Sometimes, if the light is particularly strong and the water droplets are very uniform, a fainter secondary rainbow can be seen outside the primary one. This is created by two reflections inside the water droplet, which reverses the order of the colors and makes the secondary bow noticeably dimmer. The area between the two bows, known as Alexander's band, appears darker than the sky inside or outside the arcs. A rainbow is not a physical object that can be approached. It is a pattern, an image created by the interplay of light and countless falling drops of water, a perfect circle of color whose center is the shadow of your head, and whose existence is a momentary collaboration between the sun, the rain, and your own unique perspective. When the water in the atmosphere is not liquid, but frozen into countless tiny six-sided ice crystals high in the cirrus clouds, even more elaborate light shows can emerge. These crystals, falling slowly through the stable air of the upper troposphere, often orient themselves with their large, flat faces parallel to the ground. They act like myriad floating mirrors and prisms. When the sun is low on the horizon, these crystals can refract and reflect its light to create bright spots on either side of the sun, known as sundogs or parhelia. These are patches of intense, often rainbow-colored light that flank the sun at a distance of about 22 degrees. At other times, the crystals can create a vast, faint circle of light that encircles the entire sky at the same altitude as the sun, known as the 22-degree halo. On even rarer occasions, more complex arcs and tangents can bisect the sky, creating a silent, shimmering cathedral of ice and light that can last for hours. These displays require no sound, no movement beyond the gentle drift of the clouds. They are the atmosphere's most serene art, a physics of perfection and alignment, reminding us that even in the highest, coldest parts of the sky, where no life exists, there is still a capacity for creating breathtaking beauty, a beauty that asks only for us to pause, to look up, and to appreciate the quiet, luminous wonders that the interaction of light and weather can provide. As we have journeyed through the atmosphere, from the rain-laden troposphere to the sun-drenched stratosphere, we have seen how the sun's uneven heating creates movement. This movement, on its largest scale, organizes itself into great rivers of air that flow around our planet with a consistency that has guided explorers for millennia and that continues to shape the very character of distant lands. These are the prevailing winds, the steady, planetary breaths that form the backbone of global atmospheric circulation. They are not the local, fickle breezes that rustle the leaves outside your window, but rather the deep, persistent currents that steer weather systems across oceans and continents. Their patterns were first mapped not by scientists with sophisticated instruments, but by ancient mariners who learned to read the language of the sea and the sky. They noticed that at certain latitudes, the winds blew with a remarkable and predictable constancy, and they used these aerial rivers to fill their sails and connect the world. These patterns are the direct result of the giant convection cells, the Hadley, Ferrel, and polar cells, and the ever-present influence of the Earth's rotation, which deflects these vast flows to the right in the northern hemisphere and to the left in the southern. In the tropics, between approximately 30 degrees north and 30 degrees south latitude, the most famous of these winds hold sway, the trade winds. These are the easterlies, blowing consistently from the northeast in the northern hemisphere and from the southeast in the southern. They are the outflow from the great subtropical high-pressure zones, the surface expression of the sinking air from the Hadley cells, flowing back toward the equatorial low pressure where warm air rises. For centuries, these were the winds of commerce. European sailing ships would drop south to catch the reliable northeast trades, which would carry them swiftly across the Atlantic to the Americas. To return, they would sail northward to catch the prevailing westerlies of the mid-latitudes. The trade winds are generally gentle and steady, and their constant flow across the warm tropical oceans is a primary driver of surface ocean currents, helping to push great volumes of water westward in a massive, slow-moving conveyor belt. The doldrums, a belt of calm and light variable winds near the equator where the trade winds from both hemispheres converge, was the only interruption in this reliable flow. A zone feared by ancient sailors who could be becalmed for weeks, but which we now understand as the Intertropical Convergence Zone, the engine of the world's tropical rainfall. Poleward of the trade winds, beginning around 30 to 60 degrees latitude in both hemispheres, are the prevailing westerlies. These winds blow from the southwest in the northern hemisphere and from the northwest in the southern. They are the workhorses of the mid-latitudes, the winds that steer our common weather systems, the high and low pressure areas, the cold fronts and warm fronts from west to east across the continents. If you live in North America, Europe, or much of Asia, the weather you experience most often arrives on these westerly winds. They're the reason why weather patterns in the United States typically move from the Pacific coast toward the Atlantic. They are generally stronger and more variable than the trade winds, especially in the southern hemisphere, where there is less land to disrupt their flow. Here, over the vast southern ocean, the westerlies can roar unimpeded around the globe, creating the legendary Roaring 40s, Furious 50s, and Screaming 60s, latitudes known for their ferocious winds and monstrous seas, where the air races endlessly around Antarctica, driven by the tremendous temperature difference between the frozen continent and the warmer mid-latitudes. Finally, blowing out from the permanent high-pressure zones over the ice caps are the polar easterlies. These are cold, dry, and often shallow winds that flow from the northeast in the Arctic and from the southeast in the Antarctic. They are the surface outflow of the polar cells, the air that has sunk over the poles and now moves equatorward. They are not as steady or as strong as the trade winds or westerlies, but they play a crucial role in the global circulation. They are the source of the frigid air masses that periodically spills southward into the mid-latitudes, bringing sharp drops in temperature, and when they clash with warmer air from the subtropics, creating the potent weather systems that generate much of the snow and rain for the temperate regions of the world. The boundary between the cold polar easterlies and the milder prevailing westerlies is not a smooth transition, but a steep, sloping battleground known as the polar front. It is along this frontal zone that the jet streams, those high-altitude, fast-flowing ribbons of air, race, acting as a guide for the development and movement of storms. These prevailing wind patterns are the great, enduring currents of our planetary atmosphere. They are the silent, powerful force that has distributed heat, moisture, and life across the globe for eons, connecting every continent and every ocean in a single, interconnected, and beautifully balanced system of flow. Beneath the great rivers of air flow even greater rivers of water, moving with a slow, majestic patience that makes the fastest wind seem fleeting. The oceans are the other half of the planet's circulatory system, the vast blue heart that stores and distributes the sun's energy, moderating the climate and nurturing life on a global scale. While the atmosphere moves heat vertically and horizontally through the movement of air, the oceans perform the same function through the movement of water. But they do so on a timescale that is far more gradual and with a capacity that is almost unimaginable. The sheer mass and heat capacity of seawater mean that the oceans can absorb, store, and transport an enormous amount of thermal energy. They act as the planet's great thermal flywheel, slowing the changes of the seasons near the coasts and ensuring that the temperature of the Earth remains within a range that is habitable. This moderating influence is the defining characteristic of a maritime climate, where the proximity to the ocean softens the harsh edges of temperature extremes, leading to milder winters and cooler summers than those found in the heart of the continents. The ocean's surface is warmed by the sun, particularly in the tropical latitudes. Then this warm water then begins a long, slow journey, a voyage that can last for centuries as it circulates through the deep basins of the world. This global circulation is driven by two interconnected systems: wind-driven surface currents, and the slow, deep, density-driven conveyor belt of thermohaline circulation. The surface currents are the immediate response to the wind. The prevailing winds, like the trade winds and the westerlies, drag upon the surface of the water, pushing it in great continuous streams. But due to the Coriolis effect, the water is deflected to the right of the wind direction in the northern hemisphere and to the left in the southern hemisphere. This leads to the creation of massive rotating gyres in each of the major ocean basins. In the North Atlantic, for example, the gyre flows clockwise. The North Equatorial Current, pushed west by the trades, the Gulf Stream carrying warm tropical water north along the eastern seaboard of North America, the North Atlantic Drift then steering this warmth eastward toward Europe, and finally the Canary Current flowing south to complete the circle. The Gulf Stream is perhaps the most famous of these currents, a river within the ocean so powerful that it moves more water than all the world's rivers combined. It carries warm, tropical water far to the north, releasing immense heat into the atmosphere and giving northwestern Europe a climate far milder than other regions at similar latitudes like Labrador or Alaska. Without this oceanic gift of warmth, winters in London would be as harsh as those in Moscow. But the surface is only the beginning of the story. Beneath these wind-driven currents lies the great deep ocean conveyor belt, a global system of circulation driven by differences in water density, which is itself controlled by temperature and salinity. This cold, salty water becomes so dense that it sinks, plunging down to the abyssal plains 2 or 3 miles below the surface. This sinking water acts like a plunger, pulling more water behind it and setting the deep currents in motion. From the North Atlantic, this deep, cold water flows southward, through the Atlantic, around Africa, into the Indian and Pacific Oceans. On its millennia-long journey, it slowly mixes with water above and gradually rises, eventually upwelling to the surface to complete the cycle. This global conveyor belt is the slow, beating heart of the ocean. It circulates not just heat, but also nutrients and dissolved gases like oxygen and carbon dioxide throughout the deep sea, supporting life in the dark depths and playing a critical role in regulating the Earth's climate over long periods. It is a reminder that the ocean is not a static bathtub, but a dynamic, three-dimensional volume with layers and movements that span the entire globe and operate on timescales that dwarf human history. The interaction between the ocean and the atmosphere is a continuous, intimate dance. The ocean gives up heat and moisture to the air above it, fueling the formation of clouds and storms. The atmosphere, in turn, with its winds and temperatures, shapes the ocean's currents and stirs its surface. This coupling is most dramatically evident in phenomena like El Niño, where a change in ocean temperatures alters global weather patterns. But it is also present in every gentle sea breeze, in the fog that forms over cold currents, and in the hurricanes that draw their devastating power from warm tropical waters. The oceans are the memory of the climate system, storing the sun's energy from season to season and century to century, slowly and patiently responding to changes in the atmosphere. They are the great stabilizer, the thermal reservoir that has helped keep the Earth's climate relatively stable for millennia, allowing civilization to flourish. Their deep, slow currents are the silent, rhythmic pulse of the planet, a reminder that the systems which govern our world operate with a patience and a scale that is both humbling and deeply calming. To understand weather is to understand this partnership, this eternal dance between the restless air and the profound, patient sea. Let us now turn our attention to an element of the atmosphere that is always present, though often invisible, a quiet participant in every breath we take and every change in the weather we feel. Water vapor. This is the gaseous form of water. Individual molecules liberated from the liquid by the sun's energy, now mingling unseen with the nitrogen and oxygen of the air. The amount of vapor the air can hold is not constant. It is a function of temperature, a relationship that is both simple and profound. Warm air, with its more energetic molecules, can hold a great deal of water vapor. Cool air, with its slower, more sedate molecules, has a much smaller capacity. The measure of how much vapor is actually in the air compared to how much it could hold at that temperature is what we call relative humidity. It is expressed as a percentage. When the air is holding all the vapor it possibly can at a given temperature, we say the relative humidity is 100%, and the air is saturated. This is the point where the air is full, and any additional vapor or any further cooling will force that vapor to condense back into liquid form. But relative humidity is a fickle measure, changing not only with the amount of moisture in the air, but with the temperature. A cool autumn morning might have a high relative humidity, making the air feel damp and chilly. But that same amount of actual water vapor in the air would translate to a very low relative humidity on a warm afternoon, making the air feel dry and crisp. A more constant and revealing measure is the dew point. This is the temperature to which a parcel of air must be cooled at constant pressure for it to become saturated and for condensation to begin. Unlike relative humidity, the dew point is an absolute measure of the actual amount of water vapor in the air. A high dew point means there is a great deal of moisture present. A low dew point means the air is dry. The dew point is the true indicator of how humid the air feels to us. When the dew point is high, say above 65 degrees Fahrenheit or 18 degrees Celsius, the air feels muggy and tropical because our bodies rely on the evaporation of sweat to cool down. When the air is already saturated with moisture, evaporation slows and we feel uncomfortably warm. When the dew point is low, below 50 degrees Fahrenheit, the air feels dry and comfortable, even if the temperature is quite warm, because evaporation can proceed rapidly. The dew point is also the secret architect of many familiar weather phenomena. On a clear, calm night, the ground loses heat rapidly by radiating it out into space. The air in contact with the ground cools down. If it cools to the dew point, the water vapor condenses directly onto the blades of grass, the leaves of plants, and the surfaces of cars, forming the tiny, perfect spheres of water we call dew. It is a gentle process of release, a quiet exhalation of the moisture the air could no longer hold. When the temperature at the surface drops below freezing, this process creates frost. The water vapor does not condense into liquid first, but transitions directly into ice crystals through a process called deposition, painting the world in a delicate white lace. It is a silent and beautiful transformation, the same process that creates the intricate patterns on a cold window pane. But the dew point's influence extends far beyond the ground. It is the key to understanding cloud formation. As a parcel of air rises, it expands and cools. It cools at a fixed rate known as the adiabatic lapse rate. If it continues to rise and cool, it will eventually reach its dew point temperature. At this altitude, known as the lifting condensation level, the air becomes saturated and condensation begins on microscopic particles in the atmosphere, forming a cloud. This is why flat-bottomed cumulus clouds all have their bases at roughly the same altitude across the sky. That is the lifting condensation level for that particular air mass, the invisible line where the temperature and dew point converge. The dew point is a promise of what will happen if the air is lifted or cooled. It is a hidden threshold, a temperature written into the invisible composition of the air that determines whether our days will be filled with clear skies or with the beautiful, ever-changing architecture of clouds. The concept of humidity and dew point also explains the often surprising sensations we feel in different environments. Stepping into a greenhouse, one is immediately struck by the warm, moist air. This is because plants are constantly transpiring, releasing water vapor into the enclosed space, raising the dew point and making the air feel thick and heavy. Conversely, stepping inside a building heated during a cold winter day, the air can feel extremely dry. This is because cold outdoor air, even if its relative humidity is high, holds very little actual moisture. When that air is brought indoors and heated, its capacity for moisture increases dramatically, but the actual amount of water vapor remains the same, causing the relative humidity to plummet. This is why humidifiers are often needed in winter to add moisture back into the air and raise the dew point to a more comfortable level, preventing dry skin, irritated sinuses, and static electricity. The interplay between temperature and dew point is a continuous silent dance that governs not only our large-scale weather, but also the microclimates of our homes and cities. It is a fundamental rhythm of the atmosphere, a gentle, constant process of holding and releasing of invisible vapor and visible liquid that connects the grand scale of arriving thunderhead to the single perfect drop of dew on a single blade of grass at dawn. We have explored the moisture in the air, but now we must consider the weight of the air itself, a gentle and constant force that presses upon every surface of our world and upon each of us. This is atmospheric pressure, the measure of the force exerted by the weight of the air column above a given point. At sea level, this weight is substantial, approximately 14.7 pounds per square inch, or enough to balance a column of mercury 760 millimeters tall in a barometer. We do not feel this immense weight because it is balanced by the pressure inside our bodies, but it is always there, a silent, invisible presence. This pressure is not uniform across the globe. It varies, and these variations are the fundamental drivers of the wind. Air naturally flows from areas of high pressure, where the air is sinking and accumulating, to areas of low pressure, where the air is rising and becoming less dense. It is this simple, beautiful principle that sets the air in motion, from the gentlest zephyr to the fiercest gale. The instrument that measures this pressure, the barometer, is therefore one of the most important tools in meteorology. For a falling barometer often signals the approach of a low-pressure system, then its attendant clouds and precipitation, while a rising barometer suggests the clearing skies and fair weather of an approaching high pressure. These areas of high and low pressure are not random. They are organized into large-scale systems that march across the weather maps. A high-pressure system, or anticyclone, is a region where air is gently sinking from above. As this air descends, it warms adiabatically, which increases its capacity to hold moisture and causes clouds to dissipate. This is why high pressure is typically associated with calm winds, stable conditions, and clear, sunny skies. The sinking air also tends to diverge at the surface, spinning clockwise in the northern hemisphere and counterclockwise in the southern, due to the Coriolis effect. It is a benevolent giant, bringing settled and pleasant weather. A low-pressure system, or cyclone, is its opposite. Here, air is converging at the surface and rising. As it rises, it expands and cools, leading to condensation, cloud formation, and often precipitation. Lows are the engines of much of our interesting weather. The converging air spins counterclockwise in the northern hemisphere and clockwise in the southern, drawing in moisture and energy to fuel clouds and storms. The contrast between these systems, the gentle battle between high and low, is the drama that plays out on our weather forecasts each day. The boundaries between different bodies of air, with their different temperatures and humidities, are where this drama often intensifies. These boundaries are the fronts we touched upon earlier, and they are intimately tied to pressure systems. A front marks the leading edge of a new air mass that is advancing and displacing another. The type of front is determined by the nature of the advancing air. A cold front occurs when a colder, denser air mass is advancing and wedging underneath a warmer, lighter air mass. On a weather map, it is depicted as a line with blue triangles pointing in the direction of movement. The forced uplift of the warm air along the steep slope of the front can lead to the development of dramatic, though often narrow, bands of clouds and precipitation. Towering cumulonimbus clouds that bring heavy rain, thunderstorms, and sometimes hail. The passage of a cold front is usually marked by a sudden drop in temperature, a shift in wind direction, and a sharp rise in pressure as the dense cold air moves in. A warm front, by contrast, is more gradual. It occurs when a warm air mass advances, but because it is less dense, it must ride up and over the cooler air it is replacing. It is shown on a map as a red line with semicircles. The slope of a warm front is much more gentle, leading to a wide area of clouds and precipitation that can stretch hundreds of miles ahead of the surface front. It typically brings a long period of steady, light rain or snow and a gradual increase in temperature and humidity. There are other, more subtle boundaries as well. A stationary front occurs when the boundary between two air masses is not moving, often resulting in a prolonged period of cloudy, wet weather. And a occluded front is a more complex structure that forms when a cold front catches up to a warm front, lifting the warm air entirely off the ground. These systems are common in the mature stages of a low-pressure system's life cycle. The study of these pressure systems and fronts is essentially the study of the daily weather. Forecasters track their movement, their intensity, and their interactions to predict whether our days will be filled with sunshine or showers, with calm or with wind. But on a personal level, we can often sense these changes. The ache in a joint before a storm is sometimes attributed to falling pressure. The clear, crisp air and brilliant stars of a night following a cold front passage feel different because the air is drier and denser and often cleaner, having been scoured by the wind and rain. The heavy, still air that often precedes a summer thunderstorm is the feeling of the low pressure and high humidity that fuels the coming tempest. Atmospheric pressure is the silent orchestrator, the force that, through its gentle variations across the landscape, directs the movement of the air, shapes the boundaries between different air masses, and ultimately writes the script for the ever-changing play of our weather. The gentle art of weather forecasting is a practice of observation, of understanding the patterns of the past to gently illuminate the possibilities of the future. It is not a practice of absolute certainty, but rather one of skilled interpretation, of reading the subtle signs written in the pressure, temperature, and moisture of the atmosphere. For centuries, humans have looked to the sky for clues, noting that a halo around the moon might portend rain, or that a red sky at night could suggest fair weather ahead. These were the first forecasts, born of patient observation and passed down wisdom, and they hold a kernel of truth rooted in the behavior of weather systems and the scattering of light. Today, this ancient art is supported by a vast global network of technology, satellites orbiting silently overhead, radar stations scanning the skies, weather balloons rising twice daily from hundreds of locations to sniff the upper air, and a myriad of surface stations on land and sea, all feeding a constant stream of data into powerful supercomputers. These computers run complex mathematical models that simulate the physics of the atmosphere, solving equations that describe the motion of fluids, the transfer of heat, and the transformation of water. The process begins with analysis. Meteorologists gather all the current data, the pressure readings, the temperatures, the winds, the humidities, and paint a detailed three-dimensional picture of the atmosphere at a single moment in time. This is the starting point, the initial condition for the computer models. The models then take this snapshot of the present and use their mathematical understanding of atmospheric physics to project it forward in time. They calculate how the pressure gradients will push the air, how the rising air will cool and form clouds, how the swirling vortices of low pressure will intensify or weaken. They do this not just once, but over and over again, creating a movie of the future atmosphere, frame by frame, for days ahead. But the atmosphere is a chaotic system, famously sensitive to tiny changes in initial conditions. A minuscule error in measurement, an unobserved puff of wind, can lead to vastly different outcomes over time. This is why forecasters never rely on a single model run. They use ensemble forecasting, running the same model multiple times with slightly different starting points to create a spread of possible outcomes. The forecast becomes a matter of probabilities, not certainties. A 30% chance of rain is not a guess. It is a sophisticated assessment that, based on all the available data and model runs, precipitation is expected to occur in 3 out of 10 similar atmospheric scenarios. The forecaster's role is to interpret this output, to be the human bridge between the raw numerical data of the computers and the practical needs of the public. They look for consistency among the different models and ensemble members. They apply their knowledge of local effects, how a mountain range might enhance rainfall on its windward side, how a large body of water might moderate temperatures along its shore, how a city's concrete and asphalt can create a heat island. They issue watches and warnings not based on what the models say will definitely happen, but on what is possible and what the impacts might be. A winter storm watch is issued when there is a potential for significant snow and ice, giving people time to prepare. It is upgraded to a warning when the event is imminent or occurring, when the confidence is high enough to urge action. This is a heavy responsibility, a practice that blends cold, hard data with warm human judgment. The best forecasters are those who understand both the mathematics of the models and the poetry of the sky, who can look at a satellite loop and see not just clouds, but the story of rising and sinking air, of dry slots and inflow jets. And despite the immense power of modern technology, the fundamental goal of forecasting remains beautifully simple: to reduce uncertainty and to help people make better decisions. A farmer deciding when to plant crops, a city official deciding whether to pre-treat roads for ice, a family planning a weekend picnic, all rely on this gentle art of prediction. The forecast is a conversation with the future, a best estimate based on our current understanding. Some patterns are easier to predict than others. The large-scale movement of high and low pressure systems can often be seen several days in advance. But the precise timing of a thunderstorm's development or the exact path of a snow band can remain elusive until the event is almost upon us. This is the challenge and the humility of forecasting. It is a science that acknowledges its limits, a practice that is constantly being refined and improved, yet one that will always contain an element of the unknown. It is a human endeavor to understand the atmosphere's beautiful, chaotic dance, to peer into its swirling patterns and offer a gentle suggestion of what might come next, allowing us to live in better harmony with the ever-changing sky. Our understanding of the weather, this gentle art of prediction, has itself a history as rich and layered as the atmosphere it seeks to comprehend. It is a story of evolving perception, from seeing weather as the expression of divine will to understanding it as the complex, yet knowable, interplay of physical forces. Ancient civilizations were keen observers of the sky, their lives intimately tied to its rhythms. They deified the elements, seeing the thunderstorm as the wrath of a god and the gentle rain as a blessing. The ancient Greeks made the first systematic attempts to understand atmospheric processes. Aristotle penned Meteorologica around 340 BCE, a work that gave the science its name, meteorology, meaning the study of things high in the air. While his explanations were often rooted in philosophy rather than experiment, proposing that wind was a dry exhalation of the earth and rain a wet one, he established the fundamental idea that weather was a natural phenomenon, subject to logical inquiry and not merely capricious magic. The journey toward modern understanding required instruments to measure the unseen. The invention of the thermometer, often attributed to Galileo around 1593, allowed for the quantification of temperature of hot and cold. The barometer, invented by Evangelista Torricelli in 1643, provided a way to measure the weight of the air itself, revealing the invisible pushes and pulls that drive the wind. With these tools, scientists could begin to move beyond description and into analysis. In the 17th and 18th centuries, pioneers like Robert Boyle and Jacques Charles uncovered the gas laws that describe the relationship between the pressure, temperature, and volume of air, providing the fundamental physical principles that govern atmospheric behavior. This was the beginning of a profound shift. The atmosphere could be understood through mathematics and physics. It was a fluid, and its motions could, in theory, be described by equations. The 19th century saw the birth of forecasting as a practical endeavor. The invention of the telegraph in the 1840s was a revolution. For the first time, weather observations from distant locations could be collected almost instantly, allowing for a synoptic view, a snapshot of weather conditions across a wide area at the same time. This made it possible to see storms moving across a continent. The first official weather forecasting service is often credited to Admiral Robert Fitzroy of the British Royal Navy in the 1850s. Aided by the telegraph, he began issuing storm warnings for sailors, coining the term weather forecast. He faced skepticism and even ridicule. To many, predicting the weather still seemed like arrogance, an attempt to divine the unknowable. But the value of his warnings for saving lives and property soon became apparent. This era also saw the development of the first weather maps, which plotted pressure, temperature, and wind, allowing forecasters to visually identify the patterns of highs, lows, and fronts that Wilhelm Bjerknes and the Norwegian school would so brilliantly describe in the early 20th century, giving us the conceptual model of cyclones and air masses that we still use today. The 20th and 21st centuries have been defined by an explosion of technology that has transformed meteorology from a regional practice into a global science. The development of radio allowed for the broadcasting of forecasts and the collection of data from ships at sea. The single greatest advancement was the launch of the first weather satellite, TIROS-1, in 1960. For the first time, humanity could look down upon the weather from above, watching the majestic swirl of storms across entire ocean basins, tracking the movement of systems that had once been invisible until they made landfall. Radar, developed during World War II, gave us the ability to see inside storms, to measure rainfall intensity and track the destructive path of tornadoes. And finally, the computer made possible the dream of numerical weather prediction, first envisioned by Lewis Fry Richardson earlier in the century. The complex equations that describe atmospheric motion could now be solved for the entire globe at incredible speed. Today, a global network of satellites, supercomputers, and sensors provides a constant stream of data, creating forecasts of astonishing accuracy, further into the future than ever imagined before. This long journey, from reading the signs in the sky to reading the output of a computer model, is a testament to human curiosity and perseverance. It is the story of our relationship with the air that surrounds us, a relationship that has deepened from one of fear and supplication to one of growing understanding and respectful prediction, allowing us to live with a little more grace within the gentle, powerful embrace of the weather. We change our trajectory to the polar regions, the Arctic in the north and the Antarctic in the south. They are realms where the atmosphere engages in its most extreme and yet profoundly silent performances. Here, the rules of weather are rewritten by cold, by darkness, and by a stark, beautiful simplicity. The most defining feature is not a type of storm, but an absence: the sun. For months on end, the sun does not rise above the horizon. This is the polar night, a long twilight that deepens into an endless night where the only light comes from the moon, the stars, and the ethereal dance of the auroras. The air grows incredibly cold, not just because of the lack of sunlight, but because the sun's rays, when they do graze the atmosphere at a shallow angle, are mostly reflected back into space by the brilliant white snow and ice. This cold air is extremely dense and heavy, and it settles over the ice caps, forming a permanent, shallow layer of intense high pressure. There is little moisture available as the ocean is frozen and the air is too cold to hold much water vapor. Thus, the polar winters are often characterized by an astonishing clarity, bitterly cold, but with skies of deep, star-filled blackness that feel infinitely vast. The silence in this cold is absolute, broken only by the wind or the crack of ice. It is a world reduced to its essentials, a study in monochrome and stillness. Yet, within the stillness, there is movement. The intense cold creates its own unique weather phenomena. Diamond dust is one of the most magical. This is not a storm, but a gentle precipitation of tiny, six-sided ice crystals that form directly in the cold, clear air near the surface. There are no clouds. The crystals form through a process of deposition, where water vapor turns directly into ice. On a calm day, these crystals drift slowly downward, glittering and shimmering in the faint light like a mist of diamonds. When the sun is just below the horizon, its light can be refracted through these crystals, creating brilliant colored spots of light on either side of the sun, called sundogs or parhelia, and sometimes forming a perfect luminous halo around the sun. Another phenomenon is ice fog, which occurs when the air becomes so cold that any moisture introduced into it, from human breath, from an open water lead in the sea ice, or from engine exhaust, instantly freezes into a suspension of tiny ice particles, creating a thick fog that can glitter in the light of a vehicle or a street lamp. A fog made not of water droplets, but of ice. Then, of course, there are the auroras, the northern and southern lights. This is perhaps the most famous and awe-inspiring of all polar weather-related displays, though its origins lie 93 million miles away on the sun. The sun constantly emits a stream of charged particles, the solar wind. When these particles are funneled by Earth's magnetic field toward the poles, they collide with atoms and molecules in the upper atmosphere. These collisions excite the atmospheric particles, and when they return to their normal state, they release the energy in the form of light. Oxygen molecules emit a greenish or sometimes a deep red light. Nitrogen produces blue and purple hues. The result is a silent, shimmering curtain of light that dances across the sky, flowing and fading, pulsating and swirling. It is a celestial ballet, utterly silent, a display of pure energy and color that can inspire a sense of wonder and humility that is almost overwhelming. It is weather on a cosmic scale, a direct connection between our atmosphere and our star. When the sun finally returns after the long winter, it does not set for months. This is the polar day, or midnight sun. The weather changes character. The constant sunlight provides a feeble but continuous source of heat, melting the surface of the snow and ice and creating a world of dazzling brightness and reflected light. The temperature might only rise a few degrees above freezing, but the effect is significant. The stark, dry cold of winter gives way to a damp, humid cold. Fog becomes frequent as moist air forms over the patches of open water and flows over the still chilled ice. The relentless light can be disorienting, but it also fuels a frantic burst of life. The polar regions, so often thought of as barren, reveal themselves during this time to be teeming. Algae bloom on the ice, migratory birds arrive in vast numbers, and animals emerge to raise their young. The weather is never warm, but it is dynamic, a constant interplay between the weak sun and the massive reservoir of cold stored in the ice. The polar regions are a testament to the atmosphere's adaptability, a demonstration of how the same basic principles of physics, the sun's energy, the movement of air, the phase changes of water, can create environments of such extreme and serene beauty, places where the weather is not a daily forecast, but a powerful, enduring, and deeply peaceful force that shapes every aspect of existence. In the great rhythmic breathing of the planet, few phenomena are as profound, as life-giving, and as deeply anticipated as the monsoon. It is not merely a season of rain, it is a monumental seasonal reversal of winds, a heartbeat of the climate system that brings the promise of water to billions of people and transforms entire landscapes from parched brown to vibrant green. The word itself comes from the Arabic mausim, meaning season, and it describes a wind system that changes direction with the passing of the year. Unlike the localized thunderstorms at the mid-latitudes, the monsoon is a continental-scale event, a direct and powerful response to the differential heating between land and ocean. It is the atmosphere's way of balancing the scales on a grand level, a gentle yet mighty act of bringing the ocean's abundance to the land's need. The process begins with the sun's slow march across the sky. As the northern hemisphere tilts toward the sun in spring, the vast landmass of Asia begins to heat up much more rapidly than the Indian Ocean to itself. The air over the subcontinent becomes warm and buoyant, rising into the upper atmosphere and creating a vast, persistent area of low pressure at the surface. Meanwhile, over the relatively cooler ocean, the air remains denser, forming an area of high pressure. Nature, seeking equilibrium, responds to this pressure imbalance. Moisture-laden air from over the ocean begins to flow steadily toward the thermal low over the land. This is the summer monsoon, a deep, moist, and steady flow from the southwest that advances across the Indian subcontinent, Southeast Asia, and parts of Africa. It is not a sudden storm, but a gradual, pervasive invasion of humid air. Its arrival is often preceded by weeks of intense heat as the land bakes under the sun, waiting. Then come the first signs, towering cumulonimbus clouds building on the horizon, the air growing heavy and still, and finally, the first rains, often gentle at first, then building into sustained, drenching downpours that can last for hours or days. The earth, cracked and dry, drinks deeply, and within days, the world is transformed. The life-giving power of this transformation is almost impossible to overstate. Rivers that were reduced to a trickle swell and overflow their banks. Fields that lay fallow and dusty erupt with the green shoots of newly sown rice and other crops. The monsoon is the foundation of agriculture for much of South Asia. Its timely arrival and adequate rainfall are directly linked to food security and economic stability for a significant portion of humanity. The rhythm of life itself syncs to the monsoon. Planting, harvesting, and countless cultural festivals are tied to its predictable unpredictability. The rain brings relief from the oppressive heat, washes the dust from the air, and fills the reservoirs that must last through the dry months. It is a time of celebration, of renewal, of hope. The sound of the rain on the roof becomes a constant, comforting lullaby, and the smell of the wet earth, a scent known as petrichor, is the perfume of life itself returning to the land. But the monsoon is a double-edged sword. The same rains that nourish can also destroy. Too much rain, delivered too quickly, can lead to devastating floods, landslides, and the displacement of millions of people. A delayed or weak monsoon can bring drought, crop failure, and immense hardship. The monsoon is a powerful force that demands respect. Its behavior is also intricately tied to global climate patterns like El Niño and La Niña, which can enhance or suppress its intensity, making its forecasting a matter of vital national importance. By late summer, the cycle begins to reverse. The land begins to cool relative to the ocean, the pressure systems weaken and flip, and the winds slowly shift direction. The retreating monsoon, often drier and flowing from the northeast, signals the end of the rains and the beginning of the dry, clear weather of autumn and winter. The land, now nourished, begins to slowly yield its bounty. The monsoon is thus a complete cycle, a pendulum swing of the atmosphere that demonstrates the deep, intimate connection between the ocean, the land, and the air. It is a testament to the fact that weather is not just a series of isolated events, but a fundamental, rhythmic force that shapes ecosystems, cultures, and civilizations. A gentle yet powerful reminder of the generosity and the might of the natural world. Let us now turn our attention from the grand continental scale of the monsoon to the intimate, often unnoticed world of microclimates. These are small-scale areas where the climate conditions differ from the surrounding region, sometimes quite dramatically. They are the atmosphere's subtle brushstrokes, the fine details painted onto the broader canvas of regional climate. A microclimate can be as small as a single garden, a shaded courtyard, or even the space beneath a large tree. They are created by hyperlocal variations in sunlight, moisture, wind exposure, and the heat-absorbing properties of the surface itself. Understanding these gentle variations is to understand the poetry of place, the reason why the south side of a building feels so different from the north, or why frost collects in a low-lying hollow while the surrounding slope remains untouched. These pockets of unique weather are sanctuaries and nurseries, shaping the life that exists within them and offering a fascinating glimpse into how the landscape and the atmosphere engage in a continuous, quiet dialogue. The factors that create a microclimate are beautifully simple. The most important is sunlight. A south-facing slope in the northern hemisphere receives significantly more direct solar radiation than a north-facing one. This difference can be enough to extend the growing season on the south side by weeks, allow different plant species to thrive, and create a noticeably warmer environment for insects, animals, and people. Conversely, a north-facing slope remains cooler, shadier, and retains moisture longer. The type of surface also plays a crucial role. Dark asphalt in a city parking lot will absorb heat throughout the day and radiate it back through the night, creating a small island of warmth known as an urban heat island. Right next to it, a patch of green grass will stay cooler through evaporation and transpiration from its leaves. A stone wall, having absorbed the sun's heat, will continue to radiate warmth long after the sun has set, creating a cozy niche for plants that crave a little extra protection from the cold. Even the color of the soil can influence temperature, with darker soils warming faster than light ones. Topography, the shape of the land, is another master architect of microclimates. Cold air, being dense and heavy, behaves exactly like water. It flows downhill and pools in the lowest available points. This is why valley bottoms and hollows are often significantly colder on clear, calm nights than the surrounding hillsides. These are known as frost pockets, and they are where the first frost of autumn appears and the last frost of spring lingers. A gardener must know these spots to avoid planting tender species there. Conversely, a midway point on a slope often enjoys the perfect balance. It is high enough to avoid the pooling cold air, yet not so exposed as to be battered by the full force of the wind. Wind itself is a sculptor of microclimates. A sturdy hedge or a stone wall can provide a sheltered zone on its leeward side, a place where the wind's drawing and cooling influence is greatly reduced. Within this shelter, temperatures can be higher, moisture loss slower, and plants can grow that would otherwise be stunted or damaged by the constant breeze. These sheltered nooks are like rooms in an outdoor house, each with its own unique environmental conditions. Perhaps the most profound example of human interaction with microclimates is found in agriculture, particularly in viticulture. Wine grapes are exceptionally sensitive to their environment, and vintners have long understood that the subtle differences in slope, aspect, and soil within a single vineyard can produce grapes with distinctly different characteristics. A row of vines on a well-drained, sun-drenched slope will produce richer, more powerful fruit than a row just 100 yards away in a cooler, moister hollow. This concept, known as terroir, is the essence of a microclimate, the belief that the taste of a wine is a reflection of the very specific place where the grapes were grown, a place shaped by its unique interplay of weather, geology, and geography. But you need not be a winemaker to appreciate a microclimate. Anyone who has sought the cool shade of a forest on a hot day or basked in the sun-warmed bricks of a building on a cool afternoon has experienced one. They remind us that weather is not a uniform blanket, but a tapestry of countless tiny variations. They invite us to be more observant, to notice where the snow melts first, where the dew lingers longest, and where the first crocus pushes through the snow. In doing so, we become more deeply connected to the quiet, hidden rhythms of the immediate world around us, discovering a universe of meteorological wonder in our own back gardens. Beyond the physics of pressure systems and the mathematics of forecast models, weather holds a deep and quiet resonance within the human spirit. It is more than a subject of scientific inquiry. It is a constant, gentle companion to our lives, a backdrop against which our most personal moments unfold, and a powerful influence on our mood, our creativity, and our sense of connection to the world. There is a profound comfort in the rhythm of the seasons, a reassurance in the predictable turn from the rebirth of spring to the dormancy of winter. This rhythm provides a structure to our years, a series of familiar milestones: the first warm day that invites bare feet onto grass, the first crisp afternoon that calls for a sweater, the first snowfall that hushes the world. These are sensory experiences that anchor us in time and place, creating a personal tapestry of memory woven with threads of sunlight, the scent of rain on dry earth, and the sound of wind through particular trees. Weather provides a shared experience, a common reference point that connects us to our neighbors and to strangers alike. A heat wave becomes a collective trial, a blizzard a shared adventure, a perfect autumn day a universal gift. The influence of weather on our inner world is subtle yet significant. The long, gray days of winter with their limited sunlight can affect our biochemistry, leading to the melancholic mood often associated with the season. Conversely, the bright, long days of summer often bring with them a sense of energy and optimism. A sunny day can feel like a personal invitation to venture outside, to be active and social, while a rainy day can provide a gentle permission to slow down, to retreat indoors, to reflect, or to lose oneself in a book. This is not merely cultural, there is a physiological basis for it. Sunlight stimulates the production of serotonin, a neurotransmitter associated with mood elevation, and regulates our circadian rhythms, which govern our sleep and energy levels. The sound of rain, meanwhile, is a form of pink noise, which can mask disruptive sounds and promote a state of calm focus or deep relaxation. The weather provides an external rhythm that our internal rhythms naturally seek to harmonize with, a silent music that guides our energy and our emotions. This connection has always been a wellspring for art and literature. Countless poets have used weather as metaphor: a storm for inner turmoil, a clearing sky for hope, a mist for mystery. Painters have devoted their lives to capturing the fleeting effects of light through breaking clouds, the subtle colors of a sunset, or the dramatic interplay of shadow and light on a landscape. Composers have tried to translate the feeling of a pastoral scene or the fury of a tempest into sound. Weather provides a universal language for expressing the ineffable aspects of the human experience. It is a mirror for our emotions. When we feel peaceful, we might appreciate the gentle stillness of a snow-covered landscape. When we feel restless, we might identify with the wind tossing the branches of a tree. This artistic response is a form of deep listening, a way of being in conversation with the atmosphere, acknowledging its power and its beauty, and finding within it echoes of our own inner state. On a more profound level, weather can evoke a sense of awe, that humbling, expansive emotion we feel when confronted with something vast, powerful, and beyond our control. Standing on a shore as a thunderstorm gathers over the ocean, watching the lightning arc from cloud to sea, we feel a thrilling mixture of fear and wonder. gazing at the flawless expanse of a blue sky on a high mountain, or witnessing the silent, endless fall of snow in a forest, we can feel both insignificantly small and paradoxically connected to something immense and eternal. This feeling of awe is a gentle reminder that we are part of a much larger system, a planet alive with dynamic processes that operate on a scale far grander than our individual lives. It can be a deeply spiritual experience, a moment of transcendence where the boundary between self and world seems to soften. In a modern life often filled with noise and distraction, the weather offers a constant, accessible pathway to this state of wonder. It asks only that we step outside, that we look up, and that we pay attention to the ever-changing, ever-beautiful drama of the sky, allowing it to quiet our minds and lift our spirits, connecting us once again to the elemental poetry of the world we inhabit. And so, we come to the end of our journey through the gentle workings of the weather, a journey that began with a single photon of sunlight and carried us through the vast, invisible ocean of our atmosphere. We have seen how this light, falling unevenly upon our curved world, sets the air itself in motion, giving rise to the great global winds that journey endlessly from the tropics to the poles. We have followed the water as it is lifted silently from the seas, carried aloft on a rising currents, and transformed into the beautiful architecture of clouds, before returning to the earth as life-giving rain, completing the eternal cycle that nourishes every living thing. We have felt the gentle pressure of the air and seen how its subtle variations guide the paths of storms and the arrival of fair skies. We have learned the language of fronts, where different air masses meet in a slow, graceful dance that writes the story of our daily forecasts. We have marveled at the silent, high-altitude shield of the ozone layer and at the breathtaking light shows woven from mist and ice in the polar heavens. We have discovered that weather is not a chaotic force, but a symphony of interconnected processes, each note following the elegant rules of physics. It is the warm breath of the monsoon bringing renewal to a continent, the sheltered warmth of a south-facing wall in a garden, the predictable rhythm of the sea breeze, and the awesome power of a supercell thunderstorm. It is the global conveyor belt of the ocean, circulating heat over centuries, and the fleeting beauty of dew on a spider's web at dawn. It is a system of immense complexity, yet its principles are founded on simple, beautiful truths. Warm air rises, cold air sinks, water changes its state, and the earth spins, gently deflecting the winds on their course. This system has been operating for billions of years, long before we arrive to witness it, and it will continue long after we are gone, a testament to the enduring balance of our planet. But beyond the science, we have also felt the deeper resonance of weather within the human spirit. It is the backdrop to our memories, the source of our metaphors, and a constant, gentle reminder that we are part of something far larger than ourselves. The weather invites us to be present, to look up, to feel the wind on our skin, and to listen to the rain on the roof. It teaches us patience, for we cannot hurry the seasons or halt a coming storm. It teaches us humility, for despite all our understanding, its ultimate power remains beyond our control. And it offers a profound sense of connection, linking us to everyone else who feels the same sun, who shelters from the same rain, and who gazes up at the same moon. So now, as you prepare to rest, let the knowledge of this great, gentle system settle over you like a comfortable blanket. There is no need to hold on to the details, only to the feeling of wonder. The atmosphere is its own great self-regulating engine, and you are cradled safely within it. The sun will set and rise again, the winds will continue their ancient paths, and the water will cycle from sea to sky and back again. It is a system of perfect, peaceful balance. Listen to the gentle rhythm of your own breath, and know that it is part of the same eternal exchange. Allow the hum of the world outside to become a lullaby. The wind is sighing in the trees, the clouds are drifting slowly across the moon, and the great, calm machinery of the weather is turning, as it always has and as it always will. There is nothing you need to do but rest. Let the certainty of these constant, calming rhythms ease you into a deep and peaceful sleep, knowing you are perfectly and forever held in the gentle embrace of the air. Good night, and we will meet again on the next journey.